It makes the system and applications more efficient by removing the components and data services from a centralized server and placing the data closer to the edge. What is that? Well, we are talking about edge computing, and in today's video, we're gonna give you a glimpse about the latter and why focus on edge computing now. Before we start, make sure to subscribe, and if you want to read more about technological subjects, hit that bell button to receive our latest notifications. Let's get started. Edge computing is a distributed computing paradigm that brings computation and data storage closer to the location where it is needed to improve response times and save bandwidth. The origin of edge computing lies in content delivery networks that were created in the late 90s to serve web and video content from edge servers that were deployed close to users. In the early 2000s, these networks evolved to host applications and application components at the edge servers, resulting in the first commercial edge computing services that hosted applications such as dealer locators, shopping carts, real-time data aggregators, and ad insertion engines. When edge computing started making rounds of the internet, some of the articles came up with statements like, "The edge will eat the cloud," "The end of cloud computing era," "Edge computing will blow away cloud," "Edge will replace the cloud." However, these headlines might be stinging you because you just understood the cloud and the digital world came up with the more advanced solution, edge computing. But are these statements true? Well, no. Edge computing is just the extended version or advanced functionality of cloud computing. So let's simplify it more. Edge computing processes the data at the edge of the network. So, as we mentioned before, the edge computing makes the system and application more efficient. This reduces the flow of traffic to the central server and provides real-time local data analysis. One definition of edge computing is any type of computer program that delivers low latency nearer to the request. Karim Arbi defined edge computing broadly as all computing outside the cloud, happening at the edge of the network, and more specifically in applications where real-time processing of data is required. In his own definition, cloud computing operates on big data, while edge computing operates on instant data. That is a real-time data generated by sensors or users. According to the State of the Edge report, edge computing concentrates on servers in proximity to the last mile network. Edge nodes used for game streaming are known as gamelets, which are usually 1 or 2 hops away from the client. Per Anand Edwin, say the edge node is mostly 1 or 2 hops away from the mobile client to meet the response time constraints for real-time games in the cloud gaming context. Edge computing may employ virtualization technology to make it easier to deploy and run a wide range of applications on edge servers. The increase of IoT devices at the edge of the network is producing a massive amount of data to be computed at data centers, pushing network bandwidth requirements to the limit. Despite the improvements of network technology, data centers cannot guarantee acceptable transfer rates and response times, which could be a critical requirement for many applications. Furthermore, devices at the edge constantly consume data coming from the cloud, forcing companies to build content delivery networks to decentralize data and service provisioning, leveraging physical proximity to the end user. In a similar way, the aim of edge computing is to move the computation away from the data centers towards the edge of the network, exploiting smart objects, mobile phones, or network gateways to perform tasks and provide services on behalf of the cloud. By moving services to the edge, it is possible to provide content caching, service delivery, storage, and IoT management, resulting in better response times and transfer rates. At the same time, distributing the logic in different network nodes, introducing new issues and challenges. Edge computing brings analytical computational resources close to the end users, and therefore can increase the responsiveness and throughput of applications. Some applications rely on short response times, making edge computing a significantly more feasible option than cloud computing. Examples are applications involving human perception, such as facial recognition, which typically takes a human between 370 to 620 milliseconds to perform. Edge computing is more likely to be able to mimic the same perception speed as humans, which is useful in applications such as augmented reality, where the headset should preferably recognize who a person is at the same time as the wearer does. The distributed nature of this paradigm introduces a shift in security schemes used in cloud computing. In edge computing, data may travel between different distributed nodes connected through the internet, and thus requires special encryption mechanisms independent of the cloud. Edge nodes may also be resource-constrained devices, limiting the choice in terms of security methods. On the other hand, by keeping and processing data at the edge, it is possible to increase privacy by minimizing the transmission of sensitive information to the cloud. Furthermore, the ownership of collected data shifts from service providers to end users. Due to the nearness of the analytical resources to the end users, sophisticated analytical tools and artificial intelligence tools can run on the edge of the system. This placement at the edge helps to increase operational efficiency and is responsible for many advantages to the system. Additionally, the usage of edge computing as an intermediate stage between client devices and the wider internet results in efficiency savings that can be demonstrated in the following example. A client device requires computationally intensive processing on video files to be performed on external servers. By using servers located on a local edge network to perform those computations, the video files only need to be transmitted in the local network. Avoiding transmission over the internet results in significant bandwidth savings and therefore increases efficiency. Another example is voice recognition. If the recognition is performed locally, it is possible to send the recognized text to cloud rather than audio recordings. Businesses can benefit from the reduced latency with the instant access of real-time data in remote locations. The main purpose of edge computing is to decentralize data handling. If you are collecting the data from the cloud and unable to provide the expected speed and agility, then edge computing is surely the best choice. There are far too many examples of edge computing use cases to list here, so we have chosen 10 important ones. Autonomous vehicles. Autonomous platooning of truck convoys will likely be one of the first use cases for autonomous vehicles. Here, a group of trucks travel behind one another in a convoy, saving fuel costs and decreasing congestion. With edge computing, it will be possible to remove the need for drivers in all trucks except the front one, because the trucks will be able to communicate with each other with ultra-low latency. Remote monitoring of assets in the oil and gas industry. Oil and gas failures can be disastrous. Their assets therefore need to be carefully monitored. However, oil and gas plants are often in remote locations. Edge computing enables real-time analytics with processing much closer to the asset, meaning there is less reliance on good quality connectivity to a centralized cloud. Smart grid. Edge computing will be a core technology in more widespread adoption of smart grids and can help allow enterprises to better manage their energy consumption. Sensors and IoT devices connected to an edge platform in factories, plants and offices are being used to monitor energy use and analyze their consumption in real time. With real-time visibility, enterprises and energy companies can strike new deals. For example, where high-powered machinery is run during off-peak times of electricity demand. This can increase the amount of green energy an enterprise consumes. Predictive maintenance. Manufacturers want to be able to analyze and detect changes in their production lines before a failure occurs. Edge computing helps by bringing the processing and storage of data closer to the equipment. This enables IoT sensors to monitor machine health with low latencies and perform analytics in real time. In-hospital patient monitoring. Healthcare contains several edge opportunities. Currently, monitoring devices are either not connected or where they are, there are large amounts of unprocessed data from devices that would need to be stored on a third-party cloud. This presents security concerns for healthcare providers. An edge on the hospital site could process data locally to maintain data privacy. Edge also enables right-time notifications to practitioners of unusual patient trends or behaviors, and creation of a 360-degree patient dashboards for full visibility. Virtualized radio networks and 5G. Operators are increasingly looking to virtualize parts of their mobile networks. This has both cost and flexibility benefits. The new virtualized RAN hardware needs to do complex processing with a low latency. Operators will therefore need edge servers to support virtualizing their RAN close to the cell tower. Cloud gaming. Cloud gaming is a new kind of gaming which streams a live feed of the game directly to devices and is highly dependent on latency. Cloud gaming companies are looking to build edge servers as close to gamers as possible in order to reduce latency and provide a fully responsive and immersive gaming experience. Content delivery. By caching content, music, video stream, web pages at the edge, improvements to content delivery can be greatly improved. Latency can be reduced significantly. Content providers are looking to distribute CDNs even more widely at the edge, thus guaranteeing flexibility and customization on the network depending on user traffic demands. Traffic management. Edge computing can enable more effective city traffic management. Examples of this include optimizing bus frequency given fluctuations in demand, managing the opening and closing of extra lanes, and in the future, managing autonomous car flows. There is no need to transport large volumes of traffic data to the centralized cloud, thus reducing the cost of bandwidth and latency. Smart homes. Smart homes rely on IoT devices, collecting and processing data from around the house. Often this data is sent to a centralized remote server, where it is processed and stored. However, this existing architecture has problems around backhaul costs, latency, and security. By using edge computing and bringing the processing and storage closer to the smart home, backhaul and round-trip time is reduced, and sensitive information can be processed at the edge. As an example, the time taken for voice-based assistant devices, such as Amazon's Alexa, to respond would be much faster. These are just a few of the many use cases edge computing enables across multiple industries. Going forward, we may see more and more applications in healthcare, AR, VR, drones, smart cities, and many more. It even seems that the future holds the best for edge computing, and it is here to stay for many more years. With that being said, it brings us to the end of today's video. Don't hesitate to share your thoughts and opinions in the comment section below, and don't forget to subscribe. I'll see you in the next video. Take care.